Hi, my name is Dolev, and I actually want to start off by asking you to imagine the future. Perhaps you see looming skyscrapers or enormous flying vehicles. That is how science fiction like Star Trek typically depicts the future. We build bigger. But what I'm here to say is that the future in fact lies in going smaller. In fact, computers used to be bigger than the size of this room and used clunky mechanical switches. But then the discovery of a new state of matter, semiconductors, allowed us to develop electrical switches so tiny and powerful that your phone is 100 billion times faster than these mechanical computers. But how do we discover new materials in physics? You may point out powerful imaging methods, such as magnetic resonance imaging. But MRI is typically limited to sensitivities down to 1 trillion cubic nanometers, limiting the scale of our studies. In comes the nitrogen vacancy center, a point-like defect in diamond emerging as a means of nanoscale MRI, demonstrating sensitivities down to 5 cubic nanometers. That is like going from an Olympic-sized swimming pool to a single droplet of water. So how does one actually use the NV as a nanoscale sensor? Well, it turns out when you illuminate the NV with green laser, it emits red light. And the amount of red light it emits decays exponentially over time, and we call the time it takes to decay its decay time. Now, it also turns out that the NV acts like a tiny magnet. So the presence of fluctuating magnetic fields shoves the NV around and actually causes it to decay faster. And my research is figuring out how to exploit these properties. In a metal, for example, you have trillions of free electrons pinballing around, and this produces fluctuating magnetic fields which speed up the NV decay. Here, we demonstrate this effect by looking at the decay of red light over time in the presence of aluminum. When the NV is far from the aluminum, there is a slow, long decay, and when we bring the NV close, there is a fast, short decay. And with this quantitative change in decay time, we actually calculate the aluminum's electrical conductivity to within 1%. Now, we want to further manipulate this distance dependence, so we fabricated a sample of separated square aluminum blocks to see if we can spatially image and actually resolve nanoscale changes in conductivity. We scanned the NV over the sample, and when the NV is above the aluminum blocks, high conductivity, there is a fast decay, and when the NV is above the gaps, low conductivity, there is a slow decay. And we can clearly resolve these nanoscale changes. And for scale perspective here, the entire width of this scan is 1/100th of the diameter of a human hair. This is riveting. We can now move to imaging Mott insulators, an uncharted state of matter with potential to revolutionize nanoscale technology, and which exhibit analogous regions of high and low conductivity. And we now have a tool to explore materials and physics at phenomenally small scales. And if there's one thing that connects us with Star Trek, it is our insatiable need to explore. Thank you.